A clear blue sky. Suddenly, something detaches from a plane flying miles above. A frozen blue block of ice hurtles towards the ground. This isn't a myth. Aviation authorities call it blue ice, and it has, in very rare cases, crashed through roofs and cars. But the most shocking part isn't that it happens. It's that this is a sign of a critical system failure. It's what happens when things go wrong. This raises a much more important question. If dropping frozen waste is a malfunction, what is the incredibly complex system designed to do? And why is its flawless operation so critical, not just for hygiene, but for the safety of the aircraft itself? The answer is hidden behind the simple flush button in an airplane lavatory. To be clear, modern aircraft are designed specifically to prevent anything from being dumped overboard. The blue ice incidents that aviation authorities have documented are not a feature. They are a critical failure. This phenomenon occurs when a supposedly sealed system is breached. On the exterior of the aircraft, there is a service panel where ground crews connect a hose to empty the waste tank. If this external port or its seals are faulty, a small amount of the blue disinfectant liquid, mixed with waste, can begin to leak during flight. At a cruising altitude of 35,000 feet, the outside air temperature can plummet to 55 degrees below 0 Celsius. This escaping liquid doesn't just drip away, it freezes instantly upon contact with the fuselage. As the flight continues, more liquid seeps out, freezing in layers and slowly building a solid mass of ice. This process can continue for hours, turning a seemingly insignificant drip into a heavy, dense projectile. Eventually, a change in air pressure during descent, or simply the forces of drag, can cause this block to break off and fall. The very existence of blue ice highlights the immense pressure engineers are under. They must design a system that is absolutely leak-proof, not just for hygiene inside the cabin, but for the safety of everything on the ground below. If a tiny leak on the outside of the plane presents this much of a hazard, it underscores the even greater challenge of safely containing hundreds of gallons of waste inside a pressurized cabin. To understand the genius of the modern solution, we first have to look back at a time when the solution was far more primitive and far more direct. In the pioneering days of flight, the experience was one of raw adventure and glamour. But behind the luxury of early passenger cabins hid a far less elegant reality. The first airline toilets were often little more than a covered bucket with some chemicals, tucked behind a curtain. This system, known as a chemical toilet, was simple but deeply flawed. It was heavy, prone to spilling during turbulence, and the odor control was primitive at best. As flight durations stretched from minutes to hours, this solution became increasingly untenable. Simultaneously, in the world of military aviation, a more direct approach was sometimes taken. Engineers on some older, non-pressurized aircraft, like certain bombers during World War II, installed what were essentially straight pipe systems. Waste was simply vented out of the aircraft directly into the slipstream. While brutally effective, this was only possible on unpressurized planes flying at lower altitudes. It was never a viable option for the world of commercial passenger travel that was about to be born. The arrival of the jet age changed everything. Aircraft like the Boeing 707 and the Douglas DC-8 introduced pressurized cabins, allowing them to fly higher, faster, and for much longer distances than ever before. Suddenly, flights crossed oceans and continents. The old bucket system was now laughably inadequate, and venting waste from a pressurized cabin was an engineering impossibility. Airlines faced a critical challenge. They needed a lavatory system that was lightweight, used almost no water, a heavy and limited resource on an airplane, was perfectly hygienic, and above all, was completely self-contained within the aircraft. The answer they found would not come from traditional plumbing. Instead, engineers looked to the very environment the plane was flying through, preparing to harness a powerful and invisible force of physics. The solution engineers devised is both brutally simple and incredibly powerful. It's the reason for that deafening roar you hear when you press the flush button. That sound isn't a powerful pump or a rush of water. It is the sound of physics at its most raw. At cruising altitude, the cabin is pressurized to a comfortable level, equivalent to being on a mountain at about 8,000 feet. But outside, at 35,000 feet, the air is incredibly thin, creating a near vacuum. The toilet's plumbing system is directly exposed to this low-pressure environment outside the plane. When a passenger pushes the flush button, they are not activating a pump. They are opening a valve. For a fraction of a second, a direct path is opened between the relatively high-pressure cabin air and the low-pressure plumbing. This massive pressure difference creates an instant, powerful vacuum. The air in the bowl, along with its contents, is violently pulled into the pipes at speeds of hundreds of miles per hour. That's why engineers design the bowls with a non-stick coating, and why only a tiny stream of water is used, not to flush, but simply to rinse the bowl after the vacuum has done all the heavy lifting. This entire system, however, relies on the altitude-based pressure difference. So what happens when the plane is on the ground? Before takeoff or after landing, with no natural pressure differential to exploit, an electric vacuum generator kicks in, creating the suction needed to operate the system. This vacuum is an elegant solution for moving waste efficiently without heavy water tanks. But moving it is only half the battle. The waste is now traveling through the plane's plumbing at incredible speed. The final destination is a single, sealed chamber, hidden deep within the aircraft, where another chemical and engineering process begins. Once that powerful vacuum has done its job, the waste begins a high-speed journey through a network of pipes, all converging on a single destination. Buried deep within the aircraft, typically in the unpressurized rear cargo hold, is a large, centralized, and completely sealed holding tank. On a long-haul aircraft like a Boeing 777 or an Airbus A380, this tank can hold hundreds of gallons, and inside this tank is where the famous blue liquid truly works its magic. This liquid, often a chemical formula called anotech, is far more than just a dye or a deodorant. It is a powerful biocide engineered specifically for this environment. Its job is to break down solid waste and toilet paper, control the growth of bacteria, and chemically neutralize odors at their source. It ensures that the contents of the tank remain in a manageable, liquid state. After the plane lands and taxis to the gate, the final stage of this closed-loop process begins. A specialized ground servicing vehicle, often called a lavatory truck, pulls up to the aircraft. The ground crew attaches a secure, leak-proof hose to the plane's external service panel, the very same port where a faulty seal can lead to blue ice. This is a precision task. The crew pumps the contents of the holding tank into the truck and then replenishes the aircraft's tank with a fresh charge of the blue chemical, preparing it for the next flight. So the entire system is a closed loop. From the flush, to the tank, to the truck, nothing is ever intentionally released into the atmosphere. But this perfect containment raises a final, critical question. We have a sealed tank, being filled with waste, inside an aircraft that is constantly ascending and descending through massive changes in atmospheric pressure. What stops that tank from collapsing inward, or, worse, dangerously overpressurizing? This is where the system transcends simple plumbing and becomes a matter of life-or-death structural engineering. This brings us to the most critical and most invisible layer of engineering. That sealed waste tank is not just a simple container, it's a pressure vessel. As the aircraft ascends to cruising altitude, the atmospheric pressure outside the plane drops dramatically. If the tank were perfectly sealed with no way to compensate, this pressure difference would try to crush it inward. Conversely, during descent, as the outside pressure increases, or if gases build up inside the tank, the internal pressure could rise to a dangerous level, threatening to rupture the tank and potentially damage the aircraft's structure. To prevent this, engineers designed the tank with a series of crucial safety valves. These aren't just for emergencies, they are an active part of the system. These valves are designed to breathe, carefully venting air to equalize the pressure and ensure the tank is never under excessive stress, either positive or negative. This is why the entire system, including the vacuum generators used on the ground, has multiple layers of redundancy. A failure in one component must not lead to a catastrophic failure of the whole. The existence of a rare blue ice incident reveals a failure of an external seal, a minor problem in the grand scheme of things. But the complex engineering of the tank itself is designed to prevent a far worse scenario, a structural failure inside the aircraft. The vacuum, the sealed pipes, the chemical treatments, and the tank's pressure-regulating valves all work in concert. Their primary purpose isn't just hygiene, It's to manage physics and ensure the absolute structural integrity of the airplane. The next time you're on a flight and press that button, you'll hear the roar not as a simple flush, but as the sound of a complex and redundant safety system in action. It's a testament to the unseen engineering that keeps modern aviation incredibly safe, managing pressure, physics, and biology at 35,000 feet, all to ensure that what happens in the lavatory stays in the lavatory until it's safely on the ground.